Hello, everybody. This week we are covering chapter 7 and 8 and 9. Um, so this is our second unit, basically, from exam 1 to exam 2. There's 3 units in this class. We're now in the second one. And what you're going to find is we're going to look at a total different way of approaching how to deal with motion. In chapters 7, 8, and 9. The other chapters have to do with rotation, and we'll get to that when we get to that. But so I guess the first thing that I should say is that so far we've looked at what a force is and how acceleration, velocity, and displacement are related. We've used forces, particularly free body diagrams, to construct the motion of a system and determined its acceleration. And then from that, assuming that the forces were constant, we were able to write down equations that gave us the velocity and the displacement and use those different variables to solve for things like time. Now what we're going to do is a totally different way of looking at forces and a totally different way of looking at motion. The whole goal of this class, remember, is to observe motion of a system and then predict what that motion will be later based on our observations. And in a weird way, energy is a much easier concept to understand than forces and free body diagrams. And I hope that a lot of you will find chapters 7 and 8 much easier than everything we've done so far. When we get into rotation and torque, things get a lot harder. So the first half of this unit, 7, 8, and 9, is going to be pretty easy, I hope, for you. You might feel we've been a little dishonest, or you might wonder why we didn't teach you this first once you learn how easy it is. And it's because we needed to understand what forces were for this to work. Pardon the pun. But it's going to turn out that all we have to do is write down the energy at a couple different positions and use something called conservation of energy to almost immediately write down an equation and solve it in like 2 steps. You need to be able to do the analysis, but really it's pretty simple and pretty straightforward and easy. The derivation of it, putting all the pieces together of how this all works, is a little confusing, a little hard, a little complicated. There's a lot of extraneous stuff that we need to talk about to make sure that you understand why it all works. But the actual nuts and bolts at the end of the day, you guys are going to find unbelievably easy. At least I hope you will. One thing to remember, we're going to be talking about constant forces, always constant forces in this class. If it wasn't constant, we would have some problems. But first of all, we need to start by, much like we did with forces and acceleration and velocity and position, we need to discuss the 2 terms right here. We need to define what is work and what is energy. And then we can talk about them and see how we can use those 2 concepts to understand the motion of a system at any particular moment, not time, but at any particular position in its motion. And that's the real key here. For chapter 7 and 8, we're going to be talking about position. We're not going to be talking about time at all, it turns out, which is something that makes it super easy. There's not going to be time involved in these 2 chapters. Okay, so as I said, work and energy are a different way to understand motion. You probably all know that an object that's moving, imagine someone throws a baseball at you. If they softly lob it at you, it's super easy to catch, it doesn't hurt your hands. If they throw it as hard as they can and you try to catch it, it hurts your hands, it comes fast. Well, that's because we assume that an object in motion has this inherent quality or quantity or characteristic called energy. Energy is something that, for us, particles have because they are in motion. And if a particle isn't moving relative to us, it doesn't have any energy. That's not exactly true. You probably all know Einstein's famous E equals mc squared, which is the equivalence of mass and energy. All things have many kinds of energy. For us, though, we're going to talk about kinetic energy. And kinetic energy is the energy that an object has when it's in motion, or doesn't have because it's at rest, right? We're also going to talk about something called potential energy because they go hand in hand, but we'll talk about that later. For now, just know that we're going to assume that if something's moving, it has an energy, this quantity called kinetic energy, simply because it's in motion. And if the velocity changes, its kinetic energy will change, either positive or negative. Energy is a scalar. It's a quantity. It doesn't have a direction. It does have, we can talk about negative energy or positive energy. Better yet, what we can talk about is a positive change in energy or a negative change in energy. But really, energy is just a scalar. It's just a quantity. So how do we increase the motion, the velocity of an object? And the answer we already know is we use force. If a force is applied, that's what Newton's first law told us. If you apply a force, you change the motion of the object. When we get to chapter 9, we're going to restate Newton's laws in a totally different way than what we did before. But it turns out that one way to understand Newton's laws is if you apply a force, the velocity of the object changes. If you apply no force, the velocity of the object stays the same. You all know that as Newton's first law. Object at rest stays at rest, and object in motion stays in motion unless acted upon by a force. And the real question of chapter 7 and 8, and a different question in chapter 9, is what do we mean by applying a force? Well, in chapter 7 and 8, we mean that we apply a force over a distance. So imagine that you are standing next to a table that has a block on a frictionless surface, and you use your hand, you push this thing with a force, and it travels some distance x while you're pushing it with your hand. You've applied that force over this displacement. You've applied it for a given distance, okay? We say that that force has done work. So the work, it turns out, is actually F dotted with the change in x. And the change in x is the time that the force was being applied. Another way to think about this is you get in your car and you're stopped at a stoplight. You push on the accelerator with constant, like you put the accelerator to the floor. So the car moves at constant acceleration. And you hold the gas down while you travel 100 meters. Okay. At the end of that 100 meters, your car is now traveling with some velocity. You've changed the velocity of the car because you've done work on it. You've applied a force, which is the mass of the car times acceleration, over a certain distance. I hope that makes sense to you. And that's what work is. Those of you who have taken physics, those of you who have taken chemistry, have already probably learned the term work. In thermodynamics, which is where chemistry uses it, for like an ideal gas, we talk about work. And we talk about that when the environment or the outside air, let's say you have a balloon at some pressure, a balloon of some gas, when the volume decreases, the pressure increases because the outside air does work positive work on the gas. And if the volume is allowed to increase, the gas does positive work on the outside environment, or negative work, right? That type of work is essentially the same idea, but that's not what we're talking about. All we're talking about is that work leads to a change in the kinetic energy, and that work is a force that is applied for some distance, okay? That's it. That's all we're talking about. We need to define what kinetic energy is, and we need to define work a little bit better than we have so far. So far, we've just generally said that if you apply a force for some distance, you get a change in kinetic energy. So let's try and do a little bit better. As I said, the work done by a force is F dot X. And if you remember your dot products, A dot B is A times B times the cosine of the angle between A and B, or A cosine of the angle between them times B, which means that this is really A parallel times B, the parallel component. And what we're saying is that if we take two vectors, A and B, right, and if we want to dot them, we put them tail to tail. So imagine these are tail to tail. And what we get is we get AB is our new vector, right? And if A and B, for some reason, were at some angle to each other, right? Let me actually write that the opposite way, just to keep the cosine. A and B, then what we would take is we would take the projection of A, or AX, which is A cosine of the angle between them, and multiply that by B to get their dot product. So what this is telling us is, oh, and the final thing that we should say is if A and B are in opposite directions, right, then this angle here between them is 180 degrees, and it's negative. So we're saying that this is F component times X, right? It's a dot product. That should make sense to you. Because if they were 90 degrees off, if, for instance, A was here and B was here, or let's actually call these F and X, right? If the force were that way and the displacement of the object were that way, there's no way this force is speeding up the object in the X direction, right? So if their angles 90 degrees off each other, you get zero, okay? In order for work to be done, the force has to either be parallel, or part of it at least needs to be parallel, and part of it needs to be or anti-parallel, right? It needs to be either in the direction of X or in the opposite direction. We'll see that soon. The other thing that I should say is if these two vectors had multiple components, right? So you could have, in 3 dimensions, you could have some weird force, right, that has components in all 3 directions. If that's true, you find the work in each direction. So we're pretty much only going to deal with 1 dimensions. You can have 2 dimensions, work in 2 dimensions, and we'll talk about that. But if it were in 3 dimensions, or however many dimensions you wanted, what you would do is you'd break the force vector into, because the force vector has an fx in the I hat, plus fy in the j hat, plus fz in the z hat, or I'm sorry, in the k hat, right? And the displacement x is in the I hat, and this is in the j hat, and this is in the k hat. So what you'd have when you took the dot product of f and x is you would get f of x times x in the I hat, f of y times y, and f of z times z. That is not any more complicated than doing it in 1 dimension. So we're going to do it in 1 dimension in the lecture. I'm sure I'll probably give you a problem in the homework that you'll have to deal with 2 dimensions. but we'll talk about that later. It really doesn't complicate things any further than making you break the force into components. However, 90% of the time, we're just going to use this, and we're going to have to determine what this is sometimes. Okay, that's a lot for a really simple concept. All right, so as we said, this is f dot dx if we want to integrate to get the work. Okay, and all I've done here is I did the dot product identity, and I stated what I just stated before. So if I have a block and it's moving in this direction and I apply a force to the right and it is applied over a displacement where x is also to the right, so all of these things are to the right, then I get positive work done, right? This is going to be a positive number because cosine of theta will be 0. If the force is opposite, so let's say there's something like friction that I know the force of, and I'm still trying to change, I'm applying that, this is important, I'm applying that force of friction while it slides the distance to the right of delta x, and its velocity in general is to the right. This force is actually acting to the left even though it's being applied over a positive x distance. I hope that makes sense to you, right? As the object slides to the right, we're applying a force to the left. That means that the force and the displacement are in opposite directions and the work is negative. If the force has components, you break them up into the components, right? Another thing to remember here is that the work is the change in kinetic energy. And if this is in the same direction, this is a positive change, which means the object speeds up. And if they're in opposite directions, it's a negative change. It slows down. Okay. So let's figure out what the actual kinetic energy is. And here, what I've done is I've substituted m times a for the force. Now, in chapter 9, at the very end, we're going to see what happens if the mass were not constant. But for 7 and 8, we're going to assume, and a lot of 9, we're going to assume that the mass is constant. Once I've done that, I can pull the mass out in front. And if I remember that a is dB dt, I can substitute dB dt in for a into my integral. Furthermore, I can move this dt under either dB or dx. And when I do that, I get this. And when I know that dx dt is actually my v, right, then what this gives me is m dv v, or mv dv, is my integral for the work. That integral is super easy to do. If I put the limits as v initial, v final, and I remember that x dx, when I integrate this, is x squared over 2 plus a constant for the indefinite integral. For a definite integral, it's x squared over 2 from x final to x initial, right? So when I plug this in, I see that I get this term. And this term I identify as the change in the kinetic energy. So the kinetic energy of a particle is its mass times its velocity squared over 2. Okay? That is well known to a lot of you, I'm sure. I'm sure a lot of you already knew kinetic energy was mv squared over 2. What's important here is the work is mv squared over 2. It's a change in that. Okay? That means as if I push on an object with a force, a constant force over some distance, I get a change in the kinetic energy. Another thing to note is how this kinetic energy changes. Let's say that v is 20 meters per second, or v is 40 meters per second, or v is 200 meters per second, and let's say our mass is 2 kilograms. What is our kinetic energy? Well, I chose 2 so that this would cancel, and this is just v squared. So this is 20 times 20, that's 400. This is 40 times 40, that's 1,600. And this is 200 times 200, which is 40,000. And the reason why I've written this, we're going to talk about these units, but these are joules. The reason why I've written this is to show you that if the speed doubles, the kinetic energy actually quadruples, right? That's pretty crazy, but it's something to remember. If your speed doubles, your kinetic energy quadruples. The energy the object has gets greater and greater and greater. So the energy that a baseball has traveling at 20 meters per second, it's only a quarter of the energy it has traveling at 40 meters per second. Keep that in mind when you're driving your car around. You know, basically every meter per second ends up being 4 times greater. Pretty crazy, but keep it in mind, slow down. All right, so this derivation, physically, what I want to say is you already know it, that if you apply positive work, that means that V final squared minus V initial squared, and yeah, there's a mass here, but that this has to be positive. That means that V final is greater than V initial. And if we apply negative work, then that means the opposite. In order to have negative work, V initial has to be greater than V final. And that's pretty obvious. So a force that's applied opposite the motion slows the object down. A force that's applied in the same direction speeds the object up. One thing, and we've already seen this, but plugging that in, one thing that we can think about really fast right here is we already know for a constant acceleration, we already know this equation is true. This was one of the first equations we learned, right? Let's do something quick here. Let's divide through by 2 and then multiply by m on both sides and see what happens. On this side, well, we'll start over here. On this side, we get ma times x final minus x initial. And on this side, we get m over 2 v final squared minus v initial squared. And we can see this is exactly the work equation. This is the force times the change of x is equal to the kinetic energy final minus the kinetic energy initial. So as long as we have constant forces, this is true. It actually turns out sometimes we don't even need constant forces. But for now, constant forces, this totally holds. It's a different way of looking at the same things we've done before. It's actually an easier way because no time, right? Time's not involved in any of this. Okay, the units of energy, force times displacement. We know force is newtons, we know displacement, x is meters. Now, newtons are kilogram meters over second squared, meters are meters. If we multiply that through, we can recognize that this, where V is m meters per second, this is mass times velocity squared. There's a constant 2 thrown in, but work has units of Newton meters. Newton meters were given a name. They're called joules, after a famous scientist named Joule. Energy is a scalar. That's what it is. It's a scalar, it's a quantity. We can say the change in energy is positive or negative, right? But energy itself is a scalar. Just like mass, it's just a number, right? It's an amount. There are many types of energy. We're talking about kinetic energy, but energy always has units of newtons and meters. Turns out that not all things that have units of Newton meters are energy in a weird way, but for now, just know Newton meters are joules. If you ever forget the definition of work, it's right there in the units. It's force times meters. And if you ever forget the work energy theorem, that work is equal to the change in kinetic energy, it's right there, right? Force times distance, Newton meters, are energy. Okay. As we said before, positive work speeds up, negative work slows down. Let's look at that, okay? Let's imagine your car. You're in your car, you take off from rest, okay? And your car has a mass of 60 kilograms. I don't really care what it is. But you let it go. You hold that accelerator down for 100 meters. What we want to know, this is your delta x. This is x. This is the force, the mass of the car times its acceleration that you hold down for 100 meters. And we want to know what V final is. So what do we get? How do we do this? Well, the work we already know is force dotted with delta x is equal to mv final squared over 2 minus mv initial squared over 2. Is it going to be positive or negative? Well, it has to be positive. Why? Because we know that v final is going to speed up, right? So our force is ma. What is a? I don't know. Let's choose something. 16 meters per second squared. Okay, so that means this is ma times 100. Let me not do that. Let me leave it as delta x. I'm trying to not jump into numbers right away. Over m over 2 v final squared. Our m's will cancel, and so we get a times delta x if I move the 2 over. And then, since this is going to equal v final square, I'm going to take the square root to get v final. I know this root's going to be positive. What I'm more concerned with is inside the root had better be a positive number, right? Otherwise, I can't do this root in our class. But let's put those numbers in. 2 times 16 is 32, times 100 is 3,200, and the square root of 3,200 is 56.57. 56.57 meters per second. The kinetic energy final is m to the half times v final squared. Remember that this was 3,200. If I square this, I get 3,200. So this is 60 over 2 times 3,200, or 56.57 squared. 3,200 times 30, 9.6 or 96 kilojoules. I wrote kilojoules there, 96,000 joules. A 60 kilogram object, which is not what your car weighs. That's probably what a lot of you weigh. It's like 120 pounds, 130 pounds maybe. Traveling at 120 miles per hour has 96,000 joules of energy if it runs into you. It's a lot. But yeah, you wouldn't want to be hit by a 60 kilogram object traveling at 120 miles per hour. So this object now reaches some area with friction. So it slides for a while on this frictionless surface, and then all of a sudden it reaches this region with friction. And I'm going to say that mu is 0.3, okay, in this region of friction. No, better yet, I'm not even going to deal with mu yet. We'll deal with it later. I'm going to say that the force of friction is 40 newtons, okay? And it's pointing that way. So as the block hits this region with friction, it has a force of friction going to the left. It's still changing, delta x is still changing to the right, v is still to the right. V initial here is my 56.57. I want to know how long it takes to slide to rest with this friction force. That means V final is 0. And so the work done by the friction force is friction force times delta x is equal to mv final squared over 2 minus mv initial squared over 2. This is a dot product though, and because they're opposite, this will be negative, right? So this is actually negative friction force delta X. Or you can look at it and say, yeah, this one's negative, this one's positive, so I get a negative. This is 0, so this is negative mv naught squared over 2. Negative signs will go away. I want to know what delta X is in this equation, and from that, I see that delta X is equal to mv naught squared over 2 times the force of friction that I gave you. M was 60, force of friction was 40, so that's 60 over 80 times 56.57 times 56.57. This is 2406 meters, if you do it correctly. That's a pretty far distance, okay? That's because our original force, remember, was MA, was 60 times, well, 16. Our original force was 960 newtons, right? So F is MA, and that was 60 times 16, which is 960 newtons. Our friction force was only 40. That's why it took, 24 times the distance for this thing to stop. But this is how you use work to understand motion. There's no time here, there's only distance. We could get time because it's constant force, and we could use, what we learned before if we wanted it. We could use V final is equal to V initial plus AT and solve this for time if we want it. But in general, we don't even care about it. What we care about is the motion. We care about how far it goes before it stops, or how far we have to push it, how long we have to apply a force to get its velocity up. You care about those things in things like launching a rocket. You care about it in hitting a golf ball or a baseball. Turns out you can do those with momentum easier, but for energy, you want to find out how long, what distance you need to apply a force to get a given kinetic energy, which tells you the velocity. Right? And applying a force in the same direction does positive work, speeds up the object, increases the kinetic energy. Applying a force in the opposite direction that the object's traveling slows it down. That's pretty obvious, right? Pretty easy to understand. Well, it turns out there's a lot of subtleties. I've just done these. I did these on the previous page. So I'm going to skip that. Sorry. Got a little ahead of myself. We don't have to have constant forces. One of the sections in this chapter talks about work done by a general force. I'm going to tell you, you can skip it. If you want to do it, fine. But assuming you have some force that depends on X. So perhaps it's 8x squared minus 6x plus 14. You can find the work by integrating up this force times dx, right? And that'll give you the work done. That'll give you the change of kinetic energy of the object for a general force. You could also have a general force, right? That's something like 8 in the I hat plus 6 in the J hat minus 10 in the K hat, right? And this force, you could integrate to find the work, F dot D X and dy and dz, right? I'm sorry, don't do that. What they usually do is they say F dot dr, and what that means is that you would find the work in the X, the Y, and the Z by taking the dot product of this force with dx plus dy plus dz. And when you dot that, what that means is you get F, the component of F in the I hat times dx, and the component of F in the J hat times dy, and the component of F in the K hat times dz. And because these are unit vectors, when unit vectors are multiplied, they just become 1. This becomes f in the x dx, which that would be f of x, and this would be f of y, and this would be f of z, f of y dy, and f of z dz. Take those integrals, and then the work is, they all add together because they're just scalars. The work in each direction is the work in the x and y and z, right? They're just scalars. So how much energy it has in each direction is how much energy it has. That's pretty simple to understand. The thing about this is doing general forces, 95% of that work that you're doing in that is just integrals that you've done in calculus. I'm not particularly interested in the integrals, seeing whether or not you can perform the integrals that would be asked of you. They're simple enough integrals to do. You should know them. You might need them in electro. You might need them in 4C or 4B at various times. So you need to understand that you can take a force that has components in different directions and find the work by dotting it with each of these. This is your dr. Your dr is equivalent to dx plus dy plus dz. So you would end up dotting the component of f with the appropriate displacement and integrating. But like I said, most of the work done there is calculus. And that calculus, there's not a lot of physics involved in understanding that. And me giving you a function and having you perform an integral with a dot product in it. So we're not going to do it. I do need you to understand that the force can be broken up into its x and y components so that you get work done in the x and y or z or whatever. But as long as you understand that, we're all good. So I'm not going to assign, I don't think I'll assign any homework on this. I hope not. But if I do, it'll be a simple integral. And you just need to make sure that you know how to perform the dot product before you perform the integral. Less said about that, probably better. Okay, so now we're going to get to the root of potential energy. And we need to talk about two very special types of forces. One's an actual force, one's a type of force. The two special forces, gravity and restoring forces, are special because there's something called conservative. And we'll talk about this in a little while, but essentially, conservative forces are very special. And the work done by a conservative force is known as potential energy, not kinetic energy. So let's talk a little bit about a few things related to this. We already know that if you're standing on the surface of the earth, right, there's a force of gravity down, and we call that force mg. And it's down towards the center of the earth. What's super important is we have to assume that y is positive away from the center of the earth. Y is positive going in the opposite direction of gravity in all of these energy problems. We have to do that in order for the potential energy to be calculated correctly. And you'll see that. I'm going to get to that. But we already know this force. We met this force many, many times. This other force here, this restoring force, happens when you have, for instance, a spring attached to a block. And the block can slide back and forth on the spring but not leave the spring. Or it could be a particle trapped by some other force. But we're going to model those as springs. So let's just say it's a spring for now. That's what they're in general modeled as. And so what happens is as this block travels that way, the force pulls it back. And when it's compressing the spring pushes it the other way. And so much like when we did friction, we get this negative sign in restoring forces. And that negative sign is really to imply that restoring forces always work opposite velocity. So these are always opposite velocity. They're always opposite the displacement of the spring, actually. Whichever way the displacement is moving, the force is actually moving the opposite way, kind of. You'll see what I mean. It's better to say it's opposite the velocity. That K is something known as a spring constant. It's a constant and depends on the particular force. We'll talk about those in depth in a little while, but for now, we have these two special forces. They're special because they are conservative, and conservative forces lead to potential energy. And we'll talk about why that's called potential energy and what potential energy does for us and why we should want to even worry about it. But first, let's talk about the gravity force and potential energy for falling objects and rising objects. Again, some of you have already had physics, and you might have been introduced to work and how picking up an object, you do work, carrying an object across a room at constant velocity, you don't. We'll explain that soon. Before I get there, I want to talk about work, and I want to make sure you guys are crystal clear on how to determine the work done on an object. So before we do anything, let's talk about, take something off your desk or something out of your pocket and drop it. Drop it from rest. It falls to the ground, right? So as I said before, we know that there's a force downward called mg. We know that we have to assume that y is positive up. We're going to call this y initial, and this will be our y final. This will be our v initial, and this will be our v final. And in the case where we dropped it from rest, we're going to say this is 0, okay? So before we do anything, right, anything else, there's going to be one little wrinkle with signs in here that I really need to make sure you pay attention to this part for yourself. Don't mess up your signs. There's a way to check, and I'll show you. But we already know that the work is the force dotted with the displacement, in this case, the y. We have no x here. Now we know the force is negative mg. The displacement, though, don't put the sign on. And I know you're going to be bothered by that because I put the sign on the force of gravity, but I didn't put the sign on the displacement. Well, this thing's going from y initial to y final, and we know that y initial in all cases has to be greater than y final if we're assuming that y is positive upward, okay? So it turns out that this delta y is actually negative. Delta y is negative here from the way our picture goes, because we know that y initial is greater than y final. So this becomes negative, right? No matter how, even if y initial is 0, y final would be negative whatever, okay? Now notice that this is equal to mv final squared over 2 minus mv initial squared over 2. And we know that this thing is going to have v final greater than v initial, which means this side is going to be positive. The right side of this equation is going to be positive. This side of this equation has to be positive as well. Why? Because we have this squared here. And if this side ends up negative, or we try to take the square, we're trying to take the square root of something that's negative. We can't do that, right? Okay. Let's take this one more step further. We know that it fell from rest, so this is 0. Let's say this is 0 and this is, we'll say that y initial is 0 and y final is negative 8 meters. Okay, so what we get here, and let's say our mass is 1 kilogram, just to make it easy. What we get here, if we want to know how fast this thing's going, is we get negative 1 times 9.81 times negative 8 is equal to m over 2 times v final squared, and this was 1, right? So we get 1/2, or 2, if we multiply through. We get that v final is 2 times 8 times 9.81. The negative sign cancel. What is this? Square root. Thank gosh it's positive. Times 9.81. Square root of this answer is 12.53 meters per second. Okay. Now, because this is a square root, we can say it's positive or negative. We take the negative from the picture. We know that downward is negative, right? But an important idea here is that what is the kinetic energy? Well, the kinetic energy is 1/2 times 12.53 squared, which is essentially 1/2 times 0.5 times 12.53 times 12.53 is 78.5 joules. And notice this is positive. Its kinetic energy is positive. Initially, what was its kinetic energy? Well, V initial was 0. So initially it had no kinetic energy. So the change in kinetic energy was positive. It was 78.5 minus 0. As it fell, did gravity do positive or negative work on the object? Gravity did positive work because the displacement, the change of y, and the force were in the same direction. It did positive work, and therefore the kinetic energy increased, and therefore V final increased. And while V final is negative, we've assumed that this is negative. Because it's gone down, the magnitude increased from 0 to 12.53. Okay. In contrast, let's look at something that rises. So let's say you throw that same object. We'll say that you throw it from above your head, where y initial will be 2 meters, and you throw it up until it stops rising. So we know that y final is 0, and again, just like we've always done, V final is 0, and we're going to say that V initial was 10 meters per second. So you just throw it straight up above your head at 10 meters per second. And we want to know how high. I'm sorry, I shouldn't have called that 0. We want to know how high it goes, right? So we're going to say this is H max, for height max. So if you throw it at 10 meters per second, from the height of your shoulder at 2 meters, how high does it reach? We did this before in free fall, right? And we came up with these fun equations that told us this. We just did this a bunch. But when we use the work done by gravity, we can see it in a different way. The work done by gravity, again, F is mg and it's negative. Change of y is up, right? So y is positive up. And so we get that the work is F dotted with dy, or change of y, is equal to mv final squared over 2 minus v initial squared over 2. And note that this will be 0. So we get F is minus mg. Change of y is y final minus y initial. This is equal to negative mv naught squared over 2. Okay? And we want to know, essentially, this is H max. I'm going to call it H. We want to know what H is. So if we divide through by mg, the m's will cancel and we get v naught squared over 2g. The negative signs also cancel. And if we assume that's 2, what we get is we get y final minus y initial is negative mv naught squared over 2mg with a negative sign. If I cancel this stuff out, what I get is y final, which is h, is v naught squared over 2g plus y initial, or 10 squared over 2 times 9.81 plus 2. And that is 100 divided by 2 times 9.81 plus 2 is 7.1 meters. Okay, so all I've done here is the work. You may have noticed that this looks eerily similar to v final squared minus v initial squared is equal to minus 2g y final minus y initial. It's the same equation. Divide that by 2, divide out the m's, cancel v final, and you've got the same equation. But we've done it now with work. We've used work to find this. And that's kind of nice, kind of nice. What you need to understand is that here also, the initial kinetic energy was mv naught squared over 2. And if our m, which we haven't had to put, let's say it's 1 kilogram, this is a half times 10 squared, so it's half of 100. This would be 50 joules. And our Ke final would be 0. Okay. So the work done, here we notice that the work done was negative because F and delta Y were opposite each other. Delta Y is actually going up, F is going down. That means negative work, right? So negative work results in the object slowing down, losing kinetic energy, which is what it did. V final was 0. So V initial was greater than V final, and that means that this term was negative. It actually lost kinetic energy. It started off with 50 joules, and by the time it reached maximum height, it had no energy at all, right? 0. So as long as you understand that, we're halfway done with potential energy, okay? So as I said, let's make sure that you understand that example of the book. If I pick up a mass, it could be a book, it could be my bag, it could be a small child, whatever. You pick something up. When you pick an object up, its displacement, delta y, is positive up, but the force of gravity is down. And you're doing work against gravity, okay? And that means that the work will be negative, right? That means, what does a negative work mean? Negative work means that you have to put energy in. Energy has to be put into the system. That's what negative work means. We've said that negative work slows an object down, but another way to see it is, if you're going to fight against a force, like swimming against a current, right? That's another way to see it. Let's say you have a river that's flowing this way. If you try to swim that way, you have to put energy in. If you let it carry you, it gives you energy. So you have to fight it. When you pick up an object, you actually have to work against gravity. You have to do work in order to move an object against gravity. That work is equal to F dot delta Y. Let's say I pick up a 10 kilogram mass, 2 meters. I move it 2 meters up. Well, this is negative mg is my force, and 2 meters is my y, my delta y. So the amount of work that I've done is 10 with a minus sign times 9.81 times 2. And that is negative 196, right? 196 newtons with a negative sign. That means it costs, not newtons, I'm sorry. Negative 196 joules. I had to put in 196 joules to lift that object. Where did the 196 joules come from? Energy I had in my body, my muscles, whatever. Food I ate that day. I burned 196 joules of energy lifting that object against gravity. That's a little harder to understand. So I urge you to stop for a minute, pause the video, and make sure you understand that. when you lift something up, you're doing work against gravity. You have to put energy into that object to pull it up, right? Conversely, what happens when you let an object fall? Gravity puts energy into the object free of charge, right? Gravity supplies all the energy because the force of gravity is pulling the object in. You're lifting against gravity, right? That's kind of what's happening here. If I carry a mass at a constant height and velocity across a room, and gravity is the only force that matters, right? So my delta x is in the x direction, it's in the I hat direction, and my gravity is in the negative j direction. What work am I doing? Am I doing work? Well, remember that work is force dotted with displacement. But my force is, Fg is in the j hat direction, and my delta x is in the I hat direction. And when I dot things that are 90 degrees off each other, the angle between them, 90 degrees, gives me that the work is 0, right? If that's 90 degrees, I do no work. Why do I do no work? Because I'm not moving the object either against gravity or with gravity. If gravity were the only force, you have to imagine that, forget the fact that you've got to move it across, you've got to supply energy to make it move. Forget about you being involved. But if it was traveling straight across a frictionless floor, gravity can't be doing any work to it because the displacement's not changing in the direction of gravity or anti-parallel to the direction of gravity. It's not moving with or against gravity. Gravity's not affecting it at all. And that's the real key here to what we're trying to talk about. It's two things. If the displacement is perpendicular to the force, nothing happens. You do no work. You don't put any energy in, you don't take any energy out. Secondly, if the force is acting on the object in the same direction as the displacement, meaning the force is pulling the object down or pushing the object up or pushing it left or pushing it right, you add energy to the system. And if you're working against the force, you take energy away. I'm going to try to explain this in another way when I talk about potential energy that'll hopefully make more sense as I'm constantly talking this through. So let's talk about the work done by gravity. Okay, we know the force of gravity is always negative. It's always negative mg. If we put it into this integral, you can easily see that you get negative mg dy. And so with that negative sign, right, these things flip from the normal. So the change of the work of gravity is actually backwards. The change of kinetic energy, we said, was mv final squared over 2 minus mv initial squared over 2, which is kinetic energy final minus kinetic energy initial. This is mgh initial minus mgh final, due to the fact that we say gravity is negative downward, okay? And therefore, I should say y here, but let me change things to y. So if y final were greater than y initial, right? If it moved up, the particle would slow down, right? Y final and y initial. If, on the other hand, it drops, okay, y initial is greater than y final, the particle speeds up, and that's because the force of gravity, when y final is greater than y initial, the force of gravity is opposite the change of y. When y initial is greater than y final, the force of gravity and the change of y are in the same direction, and the particle speeds up. We have to have y be positive up in order for this to be true, and we have to have this to be true. It has to be true. You'll see why in a minute. That energy we call potential energy. And why do we call it potential energy? We call it potential energy because if nothing else is happening, and I'm holding an object suspended at any point, but suspended where I can drop it. I can drop it towards the center of the earth. I don't care if I'm on top of a building. I don't care if I'm in my room. I don't care if I'm holding it right above my lap, but if I let it go, it's going to fall, which means that it potentially has kinetic energy that's stored in it. It has the potential to gain kinetic energy. The weird thing about potential energy, though, is we can say wherever we want it to be zero, we can say it's zero. So let's say this distance is 10 meters. So we say y initial is 10 and y final is 0. Or we could say right in the middle, right, that this is 0. So y initial is 5 and y final is -5, right? It doesn't matter, because either way what we're going to get is we're going to get mg is y initial minus y final. And we can see in the first instance that this would be 10 minus 0. So this would be mg times 10. In the second, we would see we get 5 minus -5, or 10 again. So this is really just delta y of our potential energy. Why am I going through that? Because normally in these problems, you're going to want to choose for the initial y value or the final y value to be 0. Wherever you care about, you choose that to be 0. What if I asked you, after it's fallen 2 meters, what is the kinetic energy? Then you would choose y final to be -2 and y initial to be 0, or y initial to be 2 and y final to be 0. Even though this is, 10 meters, I can always set my position wherever I want. What matters is delta y. And sometimes you're going to need to figure out what delta y is. Another good example would be, imagine that this angle is 30, right? And I want this thing to slide down 4 meters. Okay, so this thing goes 4 meters and it's at 30. What I need, though, is and we'll come back to this later, but I need to know the change in y. And I say this is y initial and this is y final. Okay, well, how high is this? This is 4 sine of 30, which is, what is that, a half? 4 sine of 30 is 2. So that means that this whole side length is 2, or this is 2 and this is 0, or this is 0 and this is -2, whatever. But it means it fell a distance of 2 meters if it's on an inclined plane. Usually you'll be able to tell, like, dropping it from the top of a building, or it falls 5 meters, or whatever we're talking about, okay? But the important thing is, it's the change of y that matters. You can always assume one of those two is 0 and figure out what the other one is, whether the other one's positive or negative, depending on which one you're calling 0. Then you have to understand this whole idea here. This is what I'm saying are 0. So imagine again that we're dropping a ball or an object out of our hand. We can always say that y initial and y final, we could say that y initial was 0, and let's say this whole thing is 8 meters and this is -8. Or we could say this was 8 meters and this was 0 meters. It doesn't matter. We can always choose our 0 for our potential energy. That also means that the potential energy it has is mg y initial here and mg y final here. And the change between final minus initial is the change of the potential energy. I'm sorry, initial minus final is the work done, or the energy, right? It's the potential energy of gravity. So this, if this was a 2 kilogram mass, this is 2 times 9.81 times y initial, which we said was 8 minus 0, or it was 0 minus -8. So the energy here is 16 times 9.81, right? And 16 times 9.81 is 157 joules. One other thing I want to tell you, when you're doing exams, when you're doing quizzes for me, If you want to use, instead of G is equal to 9.81 in these problems, if you want to use that G is 10 meters per second squared, I'm okay with that because you can do the calculations faster. If I need you to use 9.81, I will tell you use 9.81. So if I plug in 10 here, I get 80 times 2, I get 160 joules. That's essentially the same answer, right? So just know that if you want to use your calculator and use G as 9.81, fine. If you don't want to use your calculator and you just want to do it with using G as 10, cool. You guys can usually handle that math in your head, right? I don't really care. That's just a side note though. Okay, so the work energy theorem, assuming there's no external forces except gravity and later spring forces, says that our change in potential energy is our change in kinetic energy because this was our work, right? And by change in potential, we mean this. So we get mg y initial minus mg y final is the change in kinetic. But here's something kind of cool. Put the finals together and put the initials together, and you get mg y initial plus mv initial squared over 2 is equal to mgy final plus mv final squared over 2. This is our energy. It's technically our mechanical energy, but this is our energy. And so what this should be telling you is that if you choose position 1 at y naught and position 2 at y final, right? You can set those energies equal to each other. You can set the potential energy of gravity and the kinetic energy at y naught equal to the potential energy of gravity and the kinetic energy at y final. Set them equal. As long as there are no external forces except gravity or spring forces, therefore, if we just have potential energy and kinetic energy, what happens is we get conservation of energy. There's nothing taking energy out of the system. There's no work taking energy out of the system. This also means that the energy can either be all potential energy, all kinetic energy, or somewhere in between, or part. And we'll talk about that soon. But essentially, what we end up with, this is it right here. This is our algorithm for doing these problems. As long as there's no friction, we just start assigning the energy at different positions and setting them equal to each other and solving for the variables we need. So the energy at each point is this. And you just write that down. You can choose your y initial or your y final to be 0 to compute this stuff, right? Because we only care about the change, which makes everything super easy. So let's just do it. We've been doing this for a while. I'm going to change it up a little bit. This is 35 meters from top to bottom, and I'm dropping it from rest. So the first thing I do is I choose 2 points. Okay, I want to know what the velocity is when it hits the ground, so I better start with A, where it begins at rest, and then figure out what the energy is at B. And all I have to do is find EA and EB and set them equal. So set EA equal to EB. No forces other than gravity except G, so I can do that. I don't have to worry about any other forces. And then all I have to do is figure out what my variables are in each one. So EA is mgy, and I'm going to call it ya, plus mva squared over 2. And I set that equal to mg yb plus mvb squared over 2. So far, the only thing I've had to figure out is my 2 positions that I want. I need to remember that y has to be positive up. And that means that whatever I choose for my y initial has to be greater than y final. And my force of gravity is going to be down. But that's already taken into account in this equation, so I don't need to worry about that. I only need to find what is YA and what is VA, what is YB and what is VB. I don't even need the mass, right? Because all my masses cancel. I can get rid of my masses. Now, I know that I dropped it from rest, and that means that VA is 0. VB is what I want. Now, you can try this 2 ways. I'm going to do it one way, you can try it the other way. I'm going to say Y initial is 35 and Y final is 0. You could also say that Y initial was 0 and Y final was negative 35. You can get the same thing. So this is 35, this is 0. And we'll see that in a second. But so knowing that, this term goes away. And what I get, right, is I get MGYA. I'm sorry. I got rid of, well, let me leave the masses in there for a minute. MGYA, this term, 0. This term, 0, because Y final or YB, if you want, is 0. And V initial, VA is 0. So this is equal to MVB squared over 2. Canceling off the masses, I see that VB squared is equal to 2GYA. And that means if I take the square root, VB is equal to 2. Let's use 10 for G. And YA is 35. This is square root of 700. 2 times 35 is 70 times 100. This is 26.5. 26.46 if you want to be a little bit more careful. Okay, downward. I know it's downward because it's dropping, right? So negative if you care. That's all you have to do. Look at this algorithm. We chose 2 relevant positions. Usually the start of the problem is your first one. So find the first position and then find the position when it has whatever you're asked for. So here we were asked for the velocity right when it hits the ground. So we knew to choose A and B, right? We knew to choose A and B there and there, right? The other thing I should say is, had we chose this to be 0 and this to be negative 35, then this term would have gone away. And what we would have gotten was 0 was MGYB plus MVB squared over 2. But since this was negative 35, if we moved it over, it would essentially be the exact same thing that we had, right? But you choose your 2 positions, you write the different types of energy. So far, we only have 2 types. We have MGY and we have MV squared over 2. And this has to be Y. This can't be X. This is only true if gravity's in the problem. If it's something sliding, and we'll see that, on a level surface, and Y is not changing, MGY is always going to be the same because Y initial and Y final, or YA and YB, or whatever you're calling them in your problem, they're all the same. So all the MGY terms would all go away because all the Y's would be the same, right? This also tells you that if it's sliding on a surface, right, and there's no external forces, what if here it's VA and here's VB? Well, this, right, is MGYB plus MVB squared over 2. And since these first terms are equal, the second terms are equal, and the second terms tell you that the velocity doesn't change. And of course it doesn't change. Nothing's putting energy into the system. Nothing's taking energy out of the system. Therefore, the kinetic energy changed. However, something much more important is happening here that I want to iterate or talk about now, and then we'll keep talking about it later. But as this thing fell, let's talk about this. As our object fell, at position A, all of its energy was MGYA. It had all of its energy was potential energy. And at B, all of its energy was MVB squared over 2, was kinetic energy. Had we chosen So what if I asked you, when y is equal to 20 meters, what is v? So we'll have a c here, and at c, yc is 20 meters, and vc, we don't know. We want to know that. So we could set either the energy at A is equal to the energy at B, but as long as gravity is the only force, they're both equal to the energy at C. So we could use either one. I'm going to use mgya. So mgya plus mba squared over 2 is equal to mgyc plus mbc squared over 2. We just do the same thing, trying to make sure that you guys get into the habit of just write down the different types of energy and then kill them as you need to kill them. So we already know that this initially was 0. We can make that go away. So what we get if we move this over is mgya minus mgyc is equal to m over 2 vc squared. All the m's cancel, throw a 2 over there, do a little algebra magic, and what you get is you get 2g ya minus yc. And this is 2, g again is 10, 35 minus 20. And what do we get? 20 times 15, square root of that answer is 17.3. 17.3 meters per second, again, downward from the picture. So we can find our velocity or our potential energy anywhere we want. Once we know A, we know the energy everywhere because the energy is always equal to the energy at A, which happens to only be potential energy. Here it has some potential energy, which is mgyc, and that, I don't remember what did we say that m was. Oh, we did. Let's imagine the m is 2 kilograms. We didn't because we didn't need it. Plus kinetic energy of mvc squared over 2. So let's actually plug in numbers here. 2 times 10 times 35, that's 700 joules. And down here, right, 2 over 2 times, what did we find? 26.46. Well, 26.46 times 26.46 is 700. So 26.46 squared, and this is 700 joules. So here, this is 2 times 10, so 20 times 20, this is 400. And this is 2 over 2, goes away. 17.3 squared is 300 and 300. And what I'm trying to show you here is, at position A, it has 700 joules of energy, although all that energy is held in potential energy. So it has 700 joules of potential energy, which means if you release it and you were to measure it at 35 meters below the point where you released it, that 700 joules of potential energy would have turned into 700 joules of real energy, okay? At some point in between, we chose C. And C, it had a little bit of potential and a little bit of kinetic. And when you add them together, you get all the energy that it had at A. What's happening is the potential energy, as it goes from A to B, is going from potential energy to kinetic energy. It's turning potential energy into kinetic energy. What's doing that? Gravity. Gravity's doing work, and the potential energy stored in the system because of gravity is turning into real kinetic energy. The weird thing about potential energy is it actual energy? Yeah, but it's weird because it's up to you where you choose your 0 and how far you care about the displacement. So it can have potential energy based on your choices. And that can turn into real energy in the problem. Also, if you imagine a ball, no air resistance, so like a rubber ball that can bounce up and down, up and down, up and down, what you would see is it would go potential, kinetic, potential, kinetic, potential, kinetic, potential, kinetic, right? It would constantly be changing between potential and kinetic energies. That's why potential energy, gravity, has potential energy, which it's a conservative force because it actually doesn't matter what path we take. The only thing that matters are the endpoints, and we'll talk about that. If not today, we'll talk about that in the next lecture, I think. So the energy tells us the final velocity and the kinetic energy of the particle. If we wanted the time to fall, we could assume that the force was constant. In the previous example, it was. So we knew, again, V final is equal to V initial minus GT, and we could just compute this. T is V final minus V initial over negative G. This was 0. Remember, our final velocity will be negative, divided by 10. The time would be 1.73 seconds for C. The time for B would be 2.65 seconds, right? Pretty simple, if you wanted it. We usually don't care about time with energy, though. It just doesn't matter. The other type of potential energy, and this is a little bit harder. This is for an object on a spring, either attached or not attached. So there's really two different cases here. And we're only going to talk about ideal springs. And what that means is that for an ideal spring, you have a mass attached to it. It's attached to a wall, frictionless surface. You haven't pulled it, you haven't compressed it, you haven't done anything to it. You say that there's an equilibrium length, but without the spring being compressed or pulled, right, stretched or compressed, X is 0 at the center of mass of the object. So when you haven't done anything with the spring is at rest. You define the X of the spring to be 0. That's our first deal. Ideal springs mean that the force is constant, and that force, as we said, is negative kx. That this is a constant of the spring. In real life, how much you pull a spring apart, k can change, right? The force can change based on how much you compress or pull a spring. We assume that these are constants. So k is a constant, and that means it's an ideal spring. This is actually Hooke's law, something called Hooke's law. You saw that in your IO lab. If you did your IO lab so far, one of the things they said I wanted you to do was that quick little experiment practice module, and they showed you Hooke's law, and you had to actually pull the spring out. So this is the equilibrium length. But really, the only thing we care about is that when the spring is in equilibrium, it's neither stretched or compressed, X is 0. And we say that if we compress the spring, so we push the block in from 0 to X final, we would say that this is negative X final. And if we stretch it, right, we would say this is positive X final, right? So when we stretch it away from the anchor point, you could also flip these 180 degrees, right? The wall could be on this side and then these signs would be flipped. But we say that the force is negative kx, the displacement is negative. So if the force is always negative, when we compress it, there's a force going the opposite way. And that force is negative kx, but you know that x is negative, so this becomes positive. If we stretch it, the force goes this way, and we know, again, negative kx, but x is positive, so of course the force is negative. This whole thing, though, is actually a model of something called a restoring force. And in nature, we see restoring forces all the time. In atoms in a lattice, as the atoms kind of vibrate around, there's a natural point where they want to sit, right? Each atom in like a bar of silver wants to sit a certain distance from its neighbors, and if it moves a little bit too far this way, it gets pulled back to the right. And if it moves a little too far this way, it gets pulled back to the left. That's a restoring force. In physics, in a lot of sciences, we model this as if it were a block on a spring because it doesn't get any simpler than that. And we assume that K is constant, that there's some constant. So we just mean a force that tends to pull the object back to an equilibrium position of 0. And we need to know the displacement from 0 of the object and the spring, okay? We'll go into that in depth as we go. So the work done by a restoring force, again, plug in this for your force. This is an easy integral. X dx is x squared over 2. Noting the negative sign, again, this flips. So now we have the change in kinetic energy was mb final squared over 2 minus mb initial squared over 2. The change in the work of gravity, sometimes they'll write a U for the potential, was mg. I need to show you this too. I don't want to confuse you though. But we needed a negative sign because it actually flipped. So what I want to write it as, be careful in your book. So I'm going to say the change of potential energy for gravity. I'm just going to write it like this: mg y initial minus mg y final. And the change of potential energy of a spring then is k x initial squared over 2 minus k x final squared over 2. And again, the work energy theorem tells us the work, which is the change of potential energy of gravity plus the change of potential energy of a spring, is equal to the kinetic energy, is the change in kinetic energy. We'll see that in a minute, but that's what we're doing here. And again, we can put all the initials in one energy and all the finals in another energy, and we'll get energy initial is equal to energy final. And then we can solve problems. So what we're doing is, before we wrote that our energy was mgy plus mb squared over 2, and we did that at every position we cared about. Now we're going to include this kx squared over 2 term as well. And that's it. That's all we have to do in chapter 7 and chapter 8. As long as we don't have friction, the restoring force also is potential. And that's because if we go back and look, right, when it's stored here, if it's at rest, it has potential energy kx squared over 2. And if it's here, it has potential energy kx squared over 2. That means that if you let go of it, it would go flying back the other way. It would go flying this way, and this potential energy would turn into kinetic energy headed to the left. If you let it go here, that potential energy would turn into kinetic energy headed right. And in fact, as it goes back and forth, its potential energy becomes kinetic energy, becomes potential. Something I don't think I mentioned is that if you push the spring in, right, some x final, so let's not call that x final though. Let's actually write it this way. So if x initial, and we're going to call this 0, is compressed negative x, and then we let it go, it's flying to the right, right, with velocity. And x is now equal to 0. And then finally, it passes 0 and it reaches x final is equal to x, okay? So at each point here, it's going to have mv squared over 2 plus kx squared over 2. Here, v is equal to 0. As it's compressed fully, the energy is kx squared over 2. Once you release it, it starts moving. And when it moves through here, since x is equal to 0, this term goes away. All of it is kinetic energy. All Ke and all potential energy. And then it finally goes all the way to the right until it stretches the spring, and all of the kinetic energy has now become all potential, and it stops moving. Okay? So it stops moving because all of the kinetic energy is now stored in the spring as potential energy kx squared over 2. This is exactly what the ball bouncing with gravity is doing, except it's doing it with a spring. It's converting potential energy to kinetic, to potential, back to kinetic, back to potential, and it's just going back and forth, back and forth, back and forth, back and forth, right? It's just going back and forth on this spring, okay? The second case that I do need to talk about here that works kind of the same way, but not really, is that you could have a spring, okay? So we usually draw it like this. And we say that if it's just sitting there, it's at y initial is 0. And then we push it down some, and we'll do this at some point. But we push it down and we compress the spring. So now, let's say K is equal to 100 Newton meters. I should have stated that if F is negative Kx, you know that K is F over X, so it has to be Newton meters. But we compress this thing, so Y final is negative, let's say it's 2 centimeters, right? Okay, and then we let it go, right? And finally, it's somewhere way above the spring. And I need to talk to you about this. So initially, if it's sitting at equilibrium, nothing's going on. Here, right, we pushed it in. So I'm going to call this A. And at A, it's at rest. Nothing's happening. Everywhere, this thing has mgy plus mv squared over 2. We have gravity, right? We don't have kinetic, or we don't have spring yet, but this will be kx squared over 2. But note that this is actually x initial is 0, y initial is 0, x final. I really should call this something else, like I should call this A and B and C and D. So y, b, and xb are both negative 0.02. X is how far I've pushed the spring in. So we have mgy plus mv squared over 2 plus kx squared over 2. And that's our energy at each point. So the energy here, if we just push it down and we hold it there for a minute, it would have mg yb plus mvb squared over 2, but it's at rest, plus kxb squared over 2. At C, it's started traveling upwards, so it does have velocity as it's shooting forward. But now, y is 0, yc is 0, and xc is 0. So we get mgyc plus mvc squared over 2 plus kxc squared over 2. This is 0 and this is 0. They're both 0. And here's the whole point of me doing this. Once it goes up to here, so my y of d, let's say, is h. I don't care what h is, it's just some positive number that's greater than 0. Here, I write mgyd plus mvd squared over 2 plus kxd squared over 2. However, in the situation where you have a particle on a spring and you're launching it off the spring, even if you're like launching it to the right, once it passes equilibrium, we assume the spring's done. Once it passes equilibrium, it's now moving with velocity and it's moving faster than the spring and it's gone. So we end up with these things called roller coaster problems or pinball type problems. But if it's not attached to the spring and you compress it and release it, once it gets to equilibrium, the spring is no longer part of the problem. So what we can see happens here is, forgetting this whole part, we compress it down and we store some potential energy in the spring. But it has some negative potential energy of gravity, right? It has some negative because it's horizontal, and gravity, right? You've allowed gravity to put some energy into the system, or better yet, it's going to have to do a little bit more work against gravity because you put it lower down, right? So the energy at B is the potential energy of gravity and the spring energy. And this will actually end up being negative. This will end up being positive because XB is negative, but it's squared. YB, though, is negative. So you get some positive energy and some negative energy. Then once it hits equilibrium, it's at y is equal to 0. We chose this to be y is equal to be 0, is equal to be 0. We could have chose this to be y is 0. And that's fine. And had we done that, then our y's and our xb's, yb would be 0, yc would be 0.02, right? And it would have been fine. To be totally honest with you, it would have totally been fine. The reason being that if we do that, the energy at C, yeah, it would be fine. So doing that, here, YD would be different, right? Because we've got a different 0. So this would be H plus 2. I'm not going to get too much into that, but you could totally change it. You can totally see that. I'm getting off track. At position D, it's going to have potential energy. It's going to have kinetic energy, but the spring's no longer part of the system. No longer part of the motion that we care about. It's not contributing anymore. It's not there anymore, right? And that's because it's not attached. And you'll see that when we do a roller coaster problem again. Okay, so moving on. There's something in your book talks about called mechanical energy. And the mechanical energy is defined as the potential energy plus the kinetic energy. I've already been calling this the energy. The energy at any time is a combination of potential and kinetic, right? As long as the system is only subject to gravitation or restoring forces, mechanical energy conserved, which means we can set energy to be 0, the 0 energy point, anywhere we want. And we can just say that it's 0. And therefore, the change in potential energy plus the change in kinetic energy, I'm sorry, I guess it should be minus. If that's equal to 0, then they're equal, right? But you already know that. That's already got to be true. That's another way of saying that the mechanical energy is conserved. It always has the same value. The only way the energy of a particle or a system could change is if we had an outside force that was either doing positive or negative work, was either supplying energy or taking energy away. So imagine you're sliding on ice. If someone pushes you further or more from behind, you'll speed up. If someone pushes you to slow you down or grabs you to slow you down, you'll slow down. But if left alone, your speed won't change. Your kinetic energy won't change. And in fact, what will happen if you go up, right, against gravity, is you do exchange some kinetic energy for gravitational potential energy, but you can always get it back by dropping in height. If you hit a spring and compress a spring, your kinetic energy turns into potential energy in the spring, but if you let the spring shoot you back the other way, it comes back. So restoring forces and gravity are conservative, and they're still conserved in your energy by the way that we model our equations. So, as I said, we get this stuff. This is your potential energy of gravity. This is your potential energy of a spring. This is your potential or your kinetic energy, your changes. So we get E initial is equal to E final, and that tells us that energy is conserved. This is our E initial, this is our E final, and in practice, we simply write down the initial energies, the final energies, 0, and we're good. All right, so here's a spring example. Well, I've already did the spring example. I guess I can, Now, I'll let you guys look through the book and see an example of a block on a spring and a block launch from spring, because next time I'm actually going to do one launching. In our next lecture on Tuesday, I'm going to show you an actual problem from start to finish at the beginning of that lecture of a particle being launched off a vertical spring. So we'll talk about that next time. So putting this all together, a particle that has gravity and spring forces, right? The types of energy it can have is it can have kinetic energy, it can have potential energy, it can have the energy of a spring. And all you have to do is at every point you write down the energy. And the energy is equal to mv squared over 2 plus mgy plus kx squared over 2. I honestly write this down every time, even though there may not be a spring in the problem, because these are the only energies we have. We're going to have friction next time, and we'll talk about what to do with friction. But if you just memorize this and you write EA and EB, and you put little subscripts on all these, and you put little subscripts on B, sorry, plus, and you set EA equal to EB is equal to EC. Things get different when we have friction, but at every point in a totally conserved system, they're all equal. So you just write the different types of energy down and set them equal to each other. Make sure you know what your variables are. And we talked about various ideas about the variables, the fact that you can choose YA to be 0 or YB to be 0, and you need to make sure that the other one is correct, that the displacement between the two is correct. So as an example of doing this, we're going to do the Atwood machine. We talked about this, you may not remember, but we talked about this, I believe, in the review. We're going to do it with energy. So if you don't remember, an Atwood machine is two masses, mass A and mass B, right? And I'm going to tell you that this is going to fall 5 meters. And so this one's going to rise 5 meters. They're going to start at rest, and I want to know if A is 10 kilograms and B is 4 kilograms. I want to know what their velocity is after they've fallen 5 meters from rest. Okay, so falling 5 meters from rest. Now, for my first, for A, right, he's going to fall, Y initial will be 0. And for B, I'm going to say that Y initial is also 0. Even though A is here and B is here, I'm going to say they're both at 0. Y final will be 5. Y final for this guy will be minus 5. This one's going to rise 5. This is going to drop 5. I know that I'm going down with my force of gravity, right? And my force of gravity is still going down. So let's talk about this for a second. And I know that V initial is 0 and V initial is 0. And I don't know V final. I want to know V final of both of these guys. And they have to be the same because they're on stretchless runners. We talked about that in our exam, right? But notice this. Gravity is going to do positive work on A because the displacement of A is down and gravity is down. So the work done on A is positive, and the work done on B is negative because gravity has to raise B up, or B is being raised against gravity. But out of all that, you really just need to write down the energy at A is MA GYA plus M, I really shouldn't have, let's call this 1, and this is position 2 for A, and this is position 1, and this is position 2, and I'll call this energy 1, plus MAV, so Y1, V1 squared over 2, plus MB GY1 plus MBV1 squared over 2, and I guess I need a B there and I need an A here, right? Okay, So the energy initially, we knew this was 0 and we knew this was 0, right? But we also chose both of them to have y1 to be 0. So y1, I guess, for B, and y1 for A, we're both 0, right? And I need to call this 2, and this 2, I guess, right? And this is B2, and this is A2. Okay, so all of these terms are 0. Energy 1 is 0. Now, energy 2, so energy 2 is again MaGYA2 plus MaVA2 squared over 2 plus MbGYB squared over 2. I'm sorry, YB squared, YB2, MbVB2 squared over 2. And a few things we got to know. YA2 is negative 5 meters. YB2 is positive 5 meters, right? YB, well, B went up 5 meters, A dropped 5 meters. And VA2 is equal to VB2, okay? So what this is equal to, so E2 is equal to GYA2 plus YB2 plus MA plus MB over 2B squared. I'm just going to call it B. And this whole thing, because E1 is equal to E2 and E1 was 0, this whole thing is 0. So I can move this stuff over and solve it for V. So I get V squared MA plus MB over 2 is equal to negative MaGYA2 minus MbGYB2, okay? Remember that, what did I say here? MA was 10, MA was 10, MB was 4 kilograms. So this is 10, and this is negative 5, right? And this is 10, and this is 10, and this is, I'm sorry, this is 4, and this is 10, and this is positive 5. So let's just solve this for a number real fast. And this is 10 plus 4, right? So this is 14 divided by 2. So if I divide the whole thing by 7, right? This is 14 divided by 2, so it's 7. Divide by 7 on both sides. So this is negative 100 times negative 5. So it's a negative 500 minus 4 times 5 is 200. So this is 7v squared minus 5 minus 200. That's positive 500. So this says that v squared is 300 divided by 7. Or v is 300 divided by 7 square root 6.55 meters per second. When we look back at this, we know he's going up 6.55 meters per second. A is dropping 6.55 meters per second. You can also see that the energy being put in by gravity doing work on mass A is positive, right? Mass A is dropping in the same direction as gravity. Its displacement is in the same direction as gravity, so it's gaining energy. Mass B is being raised up. Its displacement is opposite gravity, so its energy is coming out of the system. So this is the energy due to the work done by gravity. This is the energy due to the work done against gravity. And this is their kinetic energy. And the kinetic energy is equal to the change in potential energy, which is what we see. We also see conservation of energy at all times because the energy at 1 was 0. Therefore, all of these have to add up to 0, which they do. They have to if our algebra is right. And you can see that really the issue here is not the equation. Writing this equation down is super simple. We just wrote E1 and E2, right? We're calling them A and B, but we just wrote the types it had, and we wrote them for both of them. A, gravity, A, kinetic, B, gravity, B, kinetic, right? All we have to do is write down the types of energy each particle in the system or each mass in the system has at that particular time or moment, I guess would be a better way to say it. But we have some leeway in what we call Y. If it bugs you that I said that Y was 0 for A and Y was 0 for B when they were obviously not at the same height, you could figure out, like, if B was at -2 meters here, right? It's still only going to go up 5 meters. So if this is -2, Y final is +3 if it rises 5 meters. It doesn't matter as long as you get the displacement right at B, and the displacement Y final minus Y initial is the same for A and B because they're connected by those stretchless ropes. So the real issue here is just figuring out your variables and then setting moment 1 equal to moment 2, the energy at moment 1 equal to the energy at moment 2 to get your answer. It's much easier than doing a free body diagram, to be totally honest with you. It's less work. And once you have this equation right here, it's really easy to turn this into the constant Excel equations, because if we do this, right, what did we have here? We had M A plus MB over 2 times V final squared is equal to G Y, and this was positive and negative. So G Y M A minus MB, right? And so there's this term here that we found if we did those things, but we can note that the acceleration is the same for them, just like the V final is the same. And because V final squared minus V initial squared is equal to, and V initial was 0, is equal to 2A over Y final minus Y initial, right? Well, this is actually Y final minus Y initial. That's our Y final, because our Y initial was 0. We know that A is G, right? Therefore, 2G minus that, if we move this 2 over, right? And if we add our V initial being 0, and we divide through by MA, right? We get this MA minus MB over MA plus MB. This is actually the acceleration that we would see if we did the whole free body diagram. It's easy to see if you do it both ways. We're going to talk about that before we do our final, because usually on the final you'll have a question that you'll either have to show it with a free body diagram and an energy diagram, that the two are equivalent, or you'll have the choice of doing it with energy or doing it with a free body diagram. And it turns out that it's actually pretty easy to show that the two methods are totally equivalent, that the energy method and the free body diagram method are totally equivalent, assuming constant forces, okay? So if we have two particles, I'm not going to do this whole problem, but if we have two particles with an inclined plane, there are some really important things to talk about here. So in our normal inclined plane problem, right, where again, this is mass A and this is mass B, and we want energy 1 equal to energy 2. So we assume that this is going to slide down the incline. And here's where things are going to get a little weird and a little tricky. I may need more slides. So initially, right, the height of A you have to figure out the height of A from where it is initially to where it ends up. So what ends up happening is you're told some x and x final minus x initial, like it slides 3 meters down the incline, right? And if you have a triangle where this is 3 and this is some angle, you can find y is 3 sine of the angle, right? So you can do that to figure out the drop in this. Whatever this is, though, if this guy rises 5 meters and this guy drops 5 meters, let's say, so let's turn this into a 5, right? He's going up 5 meters, then he goes down the incline 5 meters. But the height he drops is actually 5 sine of the angle, right? So what we have to say is we have mg, ma, a1 plus ma, va1 squared over 2 plus mb, gyb plus mb, vb1 squared over 2. And this is my E1. And again, let's imagine that they're not moving. They're initially at rest. We can again say that ya1 and yb1 are 0. So we can say all of these are 0, so this is 0. In that case, ya1 is equal to yb1 is equal to va1 is equal to vb1, and they're all equal to 0. It's at rest. And we chose ya1 and yb1 to be 0. But E2 is mag ya2 plus ma va2 squared over 2 plus mb gybb2 plus mb vb2 squared over 2. However, the velocity of A down the incline, VA down the incline, right, is in the down the incline direction, okay? It's not coming off this surface, so it's down the incline. And VB2 is up in the air, right? Furthermore, as we said, YA2 is equal to x final minus x initial times sine theta. Okay, and so in this case, it's 5 sine A. But VA2 and VB2 are still equal. So we can still say that. It's just what we're going to get here is we're going to get MAG x final minus x initial. E1 is equal to E2, so 0 is equal to sine theta, right? And that is going to be negative. Why is it going to be negative? Because it's starting at y initial, and y initial will be 0, and y final will actually be negative. So we really need a negative sign here. So make sure that this is negative. That's because it's actually going to, when you move it over, be positive. But that's beside the point. MA plus MB over 2 V squared plus MBGYB2, and we know that that's 5 meters or whatever. So this being negative moves over, and what you get is MAG, I'm going to call this YA2, is equal to MA plus MB all over 2 times V squared plus MBGYB2. The reason why I wanted to draw that like that is a couple things I want to note. First of all, VA and VB being equal, VA2 and VB2, just remember that they're going in different directions, completely different directions. A is going down the incline, B is going up the incline. But we can see from this exactly what is physically happening. This potential energy is the work done by gravity in the Y direction on A. Now remember, the force of gravity is down. So the displacement of A down, which is x final minus x initial times sine theta, that is the work that gravity does on A. That amount of energy has to be equal if everything's conserved, and initially everything was 0. So whatever energy is put in by gravity as this thing slides down, remember the work is only the amount of work done in the y direction. In the x direction, right, in this direction, even though there is some displacement in the x, there's no force in the x, so it slides down, and the energy that gets put in by gravity is this value. That has to be equal to the amount of energy that is turning into kinetic energy of both of them, and the energy required to work against gravity. So this is a potential energy of, potential energy due to gravity of B. Basically, some of this energy that is getting due to the work done by gravity is becoming the potential energy stored in mass B. And some of it's becoming the kinetic energy of mass A and of mass B. And you can see that in the actual thing. But as you look at this, it's actually super simple to write down. You just write mgy plus mv squared over 2 for each object. And if there were springs involved, you would add the springs. The hard part is figuring out what your variables are and figuring out where you want to say y and y initial and y final are, x initial and x final. You got to do some of these, but they're not hard once you get that stuff down. Once you do a few of these, they're super easy. And you may find you love doing these because they're so easy, because you essentially are just writing down your equation and you're moving on. And like I said, we'll do more of these. Next time, we're going to talk about friction and do lots of examples, and we're going to talk about power and a few other things that I didn't cover out of 7. Today I covered 7 and 8, but there were chunks of things I didn't cover. And I didn't cover friction because friction pulls energy out, and if there's friction, things aren't conserved. So we're going to go back through this stuff and talk about what happens with non-conservative forces and how to deal with them. But it's pretty easy. You're going to have a quiz tomorrow. If you stayed for the whole thing, I'm sure I'll tell everyone anyway tomorrow. But you'll have a quiz on just an object rising and falling in free fall, but using energy. So I'm going to want to know the energy when it's launched, the energy at max height, and the energy when it hits the ground, which should be super easy if you understood any of this. So anyway, talk to you guys tomorrow.